everybody. Thank you for joining us. My name is Shane Murphy, Technical and Sales Director at Ashgrove Renewables. I'm joined today by John Allen, standing beside me here, and we have Connor outside answering questions if we're inundated, which we presumably will be today. Today we're going to be talking about, I suppose, the advanced heat pump philosophies. There might be some of it. We'll start off a little bit on the basic side, maybe to make a point, but we want to talk about, I suppose, on a larger scale, or maybe the philosophies are applicable both to large scale and to smaller scale. But we know that a lot of heat pumps in Ireland today are being poorly installed, maybe poorly designed, poorly commissioned, poorly operated, and we cover that really on the domestic side. We cover that in the Heat Pump Common Mistakes webinar, so we won't be going over it necessarily there. We won't be going over the domestic side of it again. But if we need to cover some of the principles, maybe we'll put it in here. So we'll jump in. The screen before that, for any of you who are not used to the seminar layout or these webinar layouts, you have a Q&A button at the bottom of your screen there. Type in your questions as soon as you can. If you have technical questions, if it's CPD points you're looking for, just let us know. We'll get back to you with those. But so John and Connor will be monitoring questions. We'll reply to you, or I'll reply to you, or John will reply to you verbally throughout the webinar, or at the end if it's not applicable to any particular part. What to expect from today, what heat pumps can do, and we'll talk about the operating envelope. This tends to be poorly understood. We look at a heat pump in much the same way as we look at a boiler. It produces heat, and sure, there's not much more to it than that. But they have a comfort envelope or comfort zone. If you push them outside of that, we're going to see a drop off in performance. We often talk about this when we're talking to the layperson. Our Volkswagen Golf is a fine, efficient car, whatever it is. If I go pulling a horse box or a silage trailer with it, we all know intuitively that's not going to work, right? And we don't need to even think about it too long. We just know, listen, you can't do that. And if you do, it's going to, number one, destroy the car maybe, or certainly it's going to affect our efficiency. We're doing it every day with heat pumps, and yet we blame the heat pump at the end of it. So we'll talk about the things that affect the operating envelope. We'll talk about the different types of heat pumps. We'll talk about energy sources. We're going to dip into the software here. So the software, we will look at it after, what we would use for sizing large heat pumps. So if we had a heat pump that was producing, or we needed to deal with a load of, I'm going to say 100 kilowatt up to whatever, 10 megawatt, whatever it is, we take a more scientific view of it than we would maybe with a boiler. The reason is these are expensive pieces of kit, and we definitely don't want to oversize them. So we want to be, I suppose, innovative in the way we approach the sizing of heat pumps. So we'll go into some of the what they're doing around Europe. Sometimes we don't need to be innovative at all. We just need to steal what is working someplace else and bring it to Ireland and apply the same thinking to our weather data or our building construction. We look at decarbonisation briefly. We're not going to be flogging that today, but just to put some numbers around it. We'll talk about heating system distribution design very briefly. I think we've covered that plenty in the past, how the distribution system negatively affects the heat pump performance if it's badly done. And then, we want to talk about this one briefly. This isn't really for maybe commercial or industrial necessarily, but there are places where with large heat pumps you definitely should turn them off, and it's kind of driven into us over the last 15 years. You can't turn off heat pumps, and it's simply untrue. We just want to take a brief look at it, and then we look at bivalent systems, or whatever you want to call them, hybrid systems where I have a heat pump and I have a backup of electricity, or I have a backup of oil or gas or whatever it is. Doesn't matter. But how would I go about sizing it? And how would I use software to help me make that decision based on science rather than based on 30-year-old rules of thumb or gut feelings? So, tiny bit about Ashgrove. We're around since 2001. We were originally, I suppose, heat pump geeks, underfloor heating, solar, all of that stuff. We're coming from the renewable energy side, as Ashgrove Renewables might suggest. In the last maybe 6, 7, 8 years, we're also doing insulation, windows, doors, and so on. So that brings us on to this SEI home upgrades frameworks, one-stop shop, community energy grants, better energy homes, all of that, warmer home scheme, etc., etc. We won't be talking about that today. We have about 20,000 heat pumps in the marketplace around Ireland and the UK. I would say any of our large ones, the ones we'll see in a second here, the kind of the 2 megawatt ones, are typically in the UK. Sorry, I need to get a drink. But we have a huge number of heat pumps in operation. We know very definitely what works and what doesn't work. And so we're not here trying to sell Mitsubishi heat pump over a Panasonic or a Daikin or whatever. That's not what today is about. It's about principles of operation, and the rules should apply to pretty much any heat pump. So we're doing heat pumps from 2 kilowatt. That might be an apartment heat pump with exhaust air heat pump or something like that, up to 2 megawatt, which is typically a large modular system. We have a lot of people in our office today. That's typically the point we're making there, is that we're accessible for phone calls, which is a huge problem across the industry. I know that. At the moment, we're maybe not performing as brilliantly as we'd like. We're inundated due to various grants coming out and so on, so we're probably not as quick as we'd like to be, but our rule here is all calls returned within an hour. So that's it. Professional network, we're still looking for plumbers around the country. At the moment, we're caught for some subcontractors in various places. And indeed probably BER assessors and maybe architects in some cases as well. Yeah. But that's more to do with the home upgrades than it is to do with large heat pumps or advanced heat pump applications. And then we do a lot of free information like what you're looking at here today. We do about 100 of these a year, various topics. I suppose the central premise here is that we want these to be educational. Obviously, somewhere along the way we get work, that's okay. But the main thing is we're trying to raise the level of awareness about, in this case, heat pumps, what things will work, what things will not work. And if you come to us, that's great. But if you were going out, hopefully you're more educated than you were this morning and making decisions accordingly. And so that's it. We have a webinar. Our next big seminar is Monday evening. Next in Mullingar, that's to do with vacant and derelict properties. If we're going to be up there early in the day, if anybody wanted to come to talk to us, even if it's actually about heat pumps, we'd be happy to talk to you. We'll be there from probably 12 o'clock on. There'll be 15 of us there on the day. We'll be setting up our presentation for the evening and all the rest, but we're there actually to meet people from I think 3 o'clock until 5:30, and there'll be 10 people available if anybody wanted to come. Ideally, we'd schedule that or talk to our crew here and let them know or let us know that you're coming. But if not, rock on, that's okay. So just some previous projects, just to give you an idea, I suppose, that we're not just, we sell heat pumps, of course we do, but we're heat pump driven by me or led by me. We're heat pump geeks here. And some of the projects here we've done around the UK. So this one you're looking at on the left here is a block of apartments in Reading, which is heat pumps. It's a combined heat and power plant. It's solar. It's all the rest of it. That was a project we did probably 6 or 7 years ago. Then we do containerized modular heat pumps. So we've done those up to 2 megawatts. So the heat pumps inside in that there, you can't really even see them in that image, but they're 100 kilowatt modules and simultaneous heating and cooling. So if we're maybe if we're refrigerating an abattoir, we can take the cooling, and from that, of course, we can produce heat, where we can heat hot water or maybe produce space heating for something else. So, and we manufacture those in Mallow, and typically, again, they're going to the UK. Various reasons why they seem to be going to the UK and not Ireland and so on, but we won't go into it. And here is a large system. It was one of the first really large systems we did. Again, 100 kilowatt modules. There's 12 of them that maybe you can see in that. 1.2 megawatt. It's lake source energy. So you can see a heat exchanger. You won't make it out in that thing, but that there is a heat exchanger. You have a series of pumps. We're taking the energy from a lake, and we're using it then to drive heat around a factory, and hot water, and drying facilities. But that's all running from on-site wind turbines, and as the wind slows down, we're able to individually slow down each of the compressors by controlling the frequency to the motors. We do all of that through our computer here, and we build all of that. So we bring in those computers and we program them from the ground up. Anyway, and then you've buffer tanks that you can't see in the right hand corner here. Anyway, we did that. I'm guessing 2014 or 15. Don't know. I don't want to think that far back, being honest. All of that to say, you're here to learn about heat pumps. We know, I suppose, a lot about heat pumps. We're not like maybe the shop who sells 5 or 10 kilowatt heat pumps and here it is, I'll hand it out over the counter to you. We love heat pumps. We know what they can do. We've learned maybe the hard way 20 years ago, sometimes what they can't do, and so on. And every day we're learning. But we certainly would consider ourselves to be knowledgeable in heat pumps. Project management and all the rest of it, and system design is also, of course, on display here, which is the other thing. So anyway, stop Shane rambling. So the cost per kilowatt hour, why are we interested in heat pumps? They're cheaper to run. That is a fact. Okay, that's the first thing to know. A lot of you are there taken aback by that statement, maybe. That is a fact. If we compare oil, and we've taken this from SEI's latest quarter one survey. Quarter one. Yeah, so we're not taking into account what's going on in the Middle East, or any of that. It'd be much higher if we were to take that in, but obviously that'd be disingenuous if we use that figure. But so compared to natural gas at 11 cent, a heat pump at a COP of, what have we taken here, 3.5?
3.5, yeah.
Yeah, so kind of an average air to water heat pump or a poor geothermal heat pump would give us a COP of 3.5. So we're certainly cheaper. There's no question about that. And I've rammed that in early. Some of you mightn't still believe me when I say that, but that's a fact. The question often is, if I put in a heat pump and I use much more kilowatt hours, well, there comes a point at which it'll all add up to a figure that was higher than my oil or gas bill last year. And so we see that quite often. The other thing, of course, is my COP there at 3.5. If I put in a good heat pump, and again, I hitch up the silage trailer to it, or whatever it is, or I don't service it, or I don't commission it, or I don't operate it correctly, well, that 8 is not going to be 8. Of course, it's going to be 11, 12, or it could be literally 28. 28 is a struggle. But it could be, we sometimes see bills ultimately over the year being 3 times what it should be. Now, that's down to I'm using more energy, the COP is lower, etc., etc. But we do see bills that literally 3 times higher than they should be, in extreme cases 4 times higher than they should be, but we do see them, and it's in no way shocking. It might be shocking to some of you that something could go so badly wrong.
Well, and it's what a lot of people are probably hearing is the heat pumps are expensive to run, and they are, and as Shane said, there's 2 main reasons for that. Number 1, they're not designed correctly, so the COP is poorly, and then number 2, people are using a lot more energy just because they're told us to leave the system run all day long, and not touch it. So we'll be going through that in a little bit more detail later on.
Good. So just to give the background here on carbon, we won't spend too much time, and again, we're not in sales mode here. These are the facts. Electricity in 2010 here, you can see the embodied carbon was 483 grams of CO2 per kilowatt hour. So each kilowatt hour you take out of your socket on the wall, let's say, has somewhere along the way, whether it is a mile away or 1,000 miles away, there was carbon went into the production of it or the transmission of it. And so 16 years ago now, Jesus, it was 483. Today, it's 226, right? So that's a vast improvement, 50% improvement. But when I put a heat pump with that at a 350% efficiency or a COP of 3.5, I simply take that 226, I divide it by 3.5, and I get 65. What's interesting is Compared to oil, obviously, you can see it over here, 321 if the oil boiler is 90% efficient. But what's interesting here is we have a long way to go in Ireland on our decarbonisation of electricity journey, and we don't need to look too far. Norway is 18 at the moment. It used to be pre-Ukraine, it used to be down at 13. Sweden, we know it used to be 17. It's now probably 22 or 23. But when I take that 18 and I divide that by 3.5, I'm down at whatever that is, 4 grams of CO2 per kilowatt hour. I'm essentially zero carbon heating, right? This is why I suppose the government is pushing heat pumps. We have a bit to go with our decarbonisation, but even today, we're at 65, we're still 80% cleaner than oil. And we've a long way to go yet in our decarbonisation. That's why it's been pushed. Obviously, there's a fuel security, fuel security. And the other thing, of course, is price. The three things that we always have to consider in the energy wholesale market: security, sustainability, and price. So that's that. No more sales than that on it. So the various types of heat pump, we won't be spending time. We're all familiar today with the air source heat pump. We'll talk about ground source. We'll talk about vertical closed loop, which is, we would have seen a lot of this 10 years ago or 20 years ago in Ireland. And then the last one, which we typically don't suggest in housing, despite the fact it's shown here in a lovely image, we don't typically like to see open loop boreholes or collectors in domestic housing. The reason is inevitably there's going to be silt and so on. We won't, as we know in Ireland, maintain it. The filters will get blocked and your COP will, or your efficiency will drop. So typically there's more maintenance here. But if you're into a bigger system where you do have a kind of a regular maintenance schedule, an open loop system, you've very much less, if that's proper English, drilling cost than maybe drilling 20 or 30 or 100 ground loops. If you have access to plenty of water, it's quite cheap. Now, you do have to take into account the running cost of that pump, and you have to make sure it's not too deep, because obviously the deeper it is, the bigger the pump is, and the higher the running cost is. And of course, that all has to come out of your efficiency or your running cost. So that's the types we'll be talking about. We'll start off with basics for 30 seconds. I'm not going to go into the vapor compression cycle or any of that stuff, but simplistically, we all have one of these fellas at home, a fridge. We never really think about what happens in the back of it. All I'm going to say to you is, I know it works, you know it works, and we're going to stop thinking about it any more than that for now, okay? But what we're essentially doing, in the same way as water will not by itself flow uphill, it'll start at the top of it, it'll flow down. Heat is the same. It'll flow from hot to cold. If I wanted to go the opposite way, the same as water, if I wanted to go uphill, I have to pump it. And in this case, what a fridge will do is it will pump heat against the hill, as it were. And I'm pumping heat from inside the cold box out into a warmer room. Refrigeration does that. We're not going to spend any more time on it. So the reason we're interested in it, by the way, of course, is that it's typically a very efficient process. So for every kilowatt I put into, in this case, I'm going to show an air source heat pump. For every kilowatt or kilowatt hour I put into the left, I'm not interchanging those there, by the way, just in case Johnny starts laughing at me. That's a mortal sin in our office. If you mix up kilowatts and kilowatt hours, there's a sackable offence on the spot. It's like mixing up miles per hour and miles. But if I put in 1 kilowatt into the left, I'm essentially using that to drive a piece of machinery that will harness 3 from outside air or outside ground or an outside river or lake or whatever it is. So I'm putting in 1, it harnesses another 3, but when I'm finished with this 1, it's driving a motor. That heat becomes reusable. So what I get out the far side is 4, right? So I put in 1, I paid for 1, I got 4 out. In this case, I'm taking 32 cents. John took that from SCAI. If I divide that by 4, because I have gotten 4 here in this case, I'm getting 8.11 cent. Now, if we were to take maybe, that's probably too high a figure today. Day rate electricity is probably a bit lower. Night rate is lower again, but we're not going to botch the figures by using those. Importantly, in this case, if our electricity is 226 grams, if I divide that by 4, there is 56 grams of CO2 attached to each kilowatt hour. So, and over the years, of course, that will get better and better. So that number, that ratio that we talked about there, 1 to 4, we call that coefficient of operating performance. You don't need to know about it too much other than it is the ratio of input to output. If I have an oil boiler and I put in a litre of oil, obviously I get heat going up the flue, I get heat coming out through the jacket of the boiler and so on. So I get 90% of it is usable or 80% of it is usable. In this case, I'm putting in 1 and I'm getting 400% out. Okay. We call that COP. Obviously, if I put in 1 here, I would like 5 out here, or I would like 6 out here, or I would like 10 out here, but I don't want 2 out there, or I don't want 1 out there. Okay? And that's the good news is that's all within our control. So we want that to be as high as possible. So in the case of a ground source heat pump, we typically have slightly higher COPs. So I'm putting in 1, I'm getting 4 here, and I'm getting 5 out the far side. Now we can see that being up as far as 7 in some cases, right? If things are properly done and if the building is well designed, the pipework is correct, we've set it up properly, we've balanced it, and the person is operating it properly, we can see this up at 7. Well, in that case, my running cost is even lower than we showed a while ago. Actually, in that case, 7 versus 3.5, it'll be 4 cent versus whatever we said, 14 for oil. So you're talking about 50 or 60 or 70% cheaper than oil. But I would have to say 7 here on the right is, I'd have to say, unusual. So, but all the same figures apply. Okay? So now, here's a graph. We won't spend too much on it, but I just wanted to put it into an ignorant graph. I'll go back one. If I have a heat pump and I'm running at 35 degrees, so this is our condensing temperature coming off the hot side of my heat pump. If I have, simplistically, I'm going to say if the outside air is 15 degrees, if I come up and hit this graph, you can see here, if I'm running the heat pump at 35 degrees into, say, underfloor heating, I have a COP of 7. Now, I should keep in mind, that's great news, Shane, at 15 degrees when it's already warm. Fair enough, point taken, but it is possible. But if I travel down along here until it gets to -5 outside, you can see my COP here now is at whatever that is, 4.4 or whatever it is. So the outside air temperature or ground temperature will affect my efficiency, right? So you can see it's quite a dramatic drop to the left. More importantly, you can do nothing. You can't control the outside temperature, but you can control the operating temperature. So if I have underfloor heating and I'm working at 35 degrees there, you can see that I am operating at we'll call it 7 of a COP. Whereas if I'm at radiators and I need to run to 50 degrees, you can see there I'm after dropping to 5. No, by the way, 5 is not bad. But again, as the outside air temperature or the ground temperature drops, you're down now to 3. So these things are within our control. That's a graph. We've taken those figures from a Swedish heat pump, Thermia, and we just transposed it then onto a graph like that. So if we're putting pipes into the ground outside, we'll say we need a kilometre of pipes buried in a field or in wells. Once I put in enough pipe, the temperature in the ground won't drop much below 10 or 8 or 6 degrees. If I don't put enough pipe into the ground, say I put in half a kilometre where I needed 1 kilometre, well, obviously I'm going to start cooling the ground. And then you can see that the ground temperature drops and you can see my efficiency starts to drop away. If I do that at the same time as I've designed the underfloor heating, the heating system wrong, so my radiators are too small, my distribution pipework is too small or whatever, and I need to run now at 50 degrees. So you can see I could be down here in one scenario at a COP of 3. If my ground collector is big enough, we'll say 10, and I'm running underfloor heating at 35, I'm up at 7. So I've halved my running costs just by good design. Same heat pump, but I've halved literally my running costs. So this is an operating envelope. Again, we took from a Thermia machine, but this will be the same for Stiebel, or it'll be the same for whoever, Wiesmann. Might be a different shape, but they will have an operating envelope that looks like this. So when I have two things in this case, is a ground source heat pump. You can see here I have a brine temperature. For any of you who don't know what the brine is the water mixture. But to stop the water from freezing on the cold side, we add antifreeze. In some places, they add salt kind of mixture that it prevents it from freezing. There is a downside, not that it matters to this graph, but when you add antifreeze to it, it reduces the amount of energy that it can transport. It decreases the specific heat capacity, therefore your pipe has to get bigger, etc. But you can see here, this is the operating envelope of this gas. It doesn't matter what it is, whatever gas it is, they'll have some sort of an operating envelope. But so you can see here, in this case, if I drop the brine temperature, so the temperature from the ground is dropping. I'm taking too much energy out of the ground. I haven't put in enough pipe work or whatever is wrong. I, number one, can't get the heat pump to operate to the temperatures maybe above, in this case, 45 degrees I've just shown there. As the air temperatures get higher or the brine temperatures get higher, I can, I suppose, get increasingly higher flow temperatures on the condensing side. But all gases will have their maximum. In this case, is showing whatever that is, 67 or whatever. But once it comes up here, we start going into what's known as high pressure alarms and the various instability issues with the gas. But they'll all have an envelope. It doesn't really matter what temperatures it's occurring at or anything else, but that's the envelope that we're happy in. If we go outside of that, the heat pump is going to have problems. This is never, in my view, is never looked at really in Ireland. Certainly on the smaller scale, but again, we're making the point, the heat pumps are, in fairness, are reliable, but there is a sensitivity about them that most people don't appreciate. And we take out a boiler, we put in this yoke, and then when it's not working after, we don't read the manual, obviously, who do that, and then we moan about it, the typical answer.
Yeah, and I suppose important to note there that the design of this is within our controls. So the brine temperature is within our control for a ground source system, because we can design the amount of pipe that goes into the ground to collect the energy. And our heating temperature is can be designed for our heating distribution system. So larger radiators in a domestic house, for example, don't need as high an operating temperature as smaller radiators do, for depending on the room. Yeah. So this is all within our control, this heating envelope, and understanding it is important for designing the elements that surround the heat pump. Yeah. And again, not going back, blaming the heat pump for not performing when we've clearly put a system in place that we're expecting it to do something outside of its operating envelope.
It never could. So there's two things there. We can either design out the problem, right? But there would be scenarios here where, if you can imagine, this is a ground source heat pump, but I could actually not be, I could be just using this heat pump to take heat from an abattoir. And imagine if I was using this and I needed to produce water at minus 15. So I have minus 15 degree water leaving my heat pump to go cooling something. Well, in that case, if I'm operating at minus 15 to cool something, the maximum temperature I can get out on the hot side here now is 50 degrees. Okay, even though the heat pump box says it can reach whatever, 67 degrees. But if I'm doing if I'm cooling at a certain temperature, it limits me on the other side. If I need more than that, but I do need the minus 15, well, that's the end of it. This heat pump can't do it.
Yeah. It's moved to a different gas then, or a heat pump that has a different gas. So it's that's the wrong heat pump for that particular application.
100%. Yeah. So I hope that point is made there, right? So here's one, and we often cover this. We certainly cover this in the domestic, because we think this is probably the single biggest predictor of success. In a domestic case anyway. Maybe we over the years we've done a lot of car showrooms, we've done a lot of swimming pools and stuff like this, where we have underfloor heating, and the carpet, you wouldn't obviously have a carpet around a swimming pool. It was a great example, Johnny, thanks for that. Blame Johnny for all those things. But so we just wanted to make the point that if I'm looking for 40 watts. So you can see here 40 watts. So this is heat flux. So this is energy output per square meter of floor area. So whether it's your house or an office or a car showroom, each square meter to keep the room warm I need 40 watts. So that wouldn't be a typically car showroom. Now 40 watts won't do you unless it's mild weather. But that's kind of typical house today that doesn't have a lot of windows. But if I put the pipes in here, you can see here pipes are in the floor at 20 centimeters apart, and I'm going to get 40 watts. But importantly, I'm running my heat pump at 35 degrees. So we know from the last few charts that that's going to give us a high COP and a lower running cost, right? The next thing is if I here want to produce 100 watts. So we see this, to give you an example, that would be the car showroom. I'm going to say 3 stories high of glazing or 2 stories high of glazing, wall-to-wall glass, or being honest, it could easily be a sunroom, which is the one we often talk about when we're talking about houses. 100 watts would be nothing unusual for a sunroom, despite the rest of the house might be 15 or 20 or 25. The sunroom is drastically different. We know that on the day that it's sunny, it's overheating, but that's no use to you in the middle of January at night when it's the heat is leaving 5 times faster through the window than it is through the wall. So if I want to produce 100 watts, and I have a carpet, I now have to go to 50 degrees here that you can see down here in the bottom. And if the pipes are at 20 centimeter spacings in the ground, I can get 80 watts. So I now can't heat the room. If I go to 6-inch centers, which would typically be the fix-all in Ireland, we've designed it, which means I put it in at 6 inches, but I didn't think any more about it, 88 watts. And if I put it in at 4-inch centers, which we practically never see in Ireland out in the industry, 96.7 watts. Now that will get me to 20 degrees. Right now, if I want 22 degrees, you can see here I'll only get 90 watts out. Either way, what we're actually starting to see here, by the way, what you can see is the floor surface temperature now is creeping away up. We're into this salmon color here, which we call peripheral zone. Peripheral zone is if I have a floor surface temperature that's 30 degrees, that's within 1 minute, you'll feel that heat through the soles of your shoes. If you have a scenario like that, there's something gone wrong, and it becomes very hard to control it. You'll get hot and cold spots all over the building. You've absolutely destroyed the efficiency of your heat pump. You've doubled or you've trebled your running cost. But more importantly, you'll have other rooms in the building that didn't need 100 watts, and they're now getting scalded. Right? We hear this all the time. Makes me cranky, and here we are trying to do webinars to make people make more educated decisions over time. Hopefully that happens. Mains pipework is critical, obviously, should go without saying, but a properly designed underfloor heating system typically has a delta T of about 4 degrees, so the water going out and the water coming back have only 4 degree difference, maybe 5. It can operate at a higher delta T, but it's harder to balance it. But of course, when I'm only dumping 4 Kelvin for each litre I'm dropping into your house, typically that's 10 or 11 or whatever it is with oil or gas boilers, my pipework now has to get 2.5 times bigger. I need to shift twice, 2.5 times the amount of water. My pipework has to get bigger. That doesn't happen, right? Anyway, so conversely, if I do have the car showroom and I don't have carpet, I have tiles here or polished concrete or whatever it is, I can get at 4-inch centers, I can get 100 watts, right, at 35 degrees. Okay, so you can see there actually, in this case, if I go back one, you can see that actually doubling up on the pipework here, I've put in the pipes at 20 centimeter spacing, so I get 40 watts. You'd think by doubling the amount of pipework, I would get double the amount of heat. I don't. I actually only get 20%. Right? The floor is now saturated. You can put in as much as you want after that. It doesn't affect it anymore. Point being, I suppose this is one of the reasons we hear about heat pumps giving trouble all the time, and in this case, is fully within our control. I'm going to skip on. So this is SEI's quarterly cost report for all the various energy sources. I suppose that's only to back up, I suppose, our calculations along. It's there. Anybody who wants to Google it, SEI cost comparisons, it's there. Now, the one that I think is a little bit on the high side is natural gas here. You can see here, I think that around 13 cents is too high. I've seen it lower than that. But
I think in general, a lot of them are high. Electricity and oil and gas are probably on the slightly higher side from what it was. So they're all kind of maybe slightly higher than we'd expect to see, but maybe they're inflated all by the same amount.
Yeah.
But that's the data gathered. They gather data over the previous quarter, and they release these figures every quarter. So there'll be another one out in at the start of April there.
Yeah. But it's used for place to go. Yeah, it's used for place to go, but it's only really to show, I suppose, that we're not botching the figures that we've used back along.
Yeah.
So yeah. So I want to give, and I'm not going to spend time at this because Johnny thinks it's beneath us. We're going to take a running cost example of a house here, 220 square meters, average glazing, high air tightness, tiled floor. So this is a well insulated house, and everything is right. Okay, with the correct radiators if it is radiators, and we don't have any coverings on it. We actually have no problem with radiators. In fact, in a lot of cases, I prefer to see radiators because if they're too small, we can change them. If the underfloor heating is badly done, we can do nothing about it. So I'm nearly at the point where it hurts me to say it, that I nearly prefer if somebody comes to us that they have radiators, because I have no faith in the underfloor heating design. And we're assuming the cylinder is correct and all the rest of it. But the running costs are calculated like this. We know that kind of what do we call that? A new house today should be 26 or less kilowatt hours, right? Unless there's an awful lot of glass, we'll say. And that translates into probably €2 to €2.50 per square meter a year as a running cost. Now, by the way, that's a fact. We know that if you do the calculations on that, and provided you haven't left your electricity slip away up to 45 cents because you haven't changed suppliers, you'll heat your home for 2 to 2.50, unless there are things done wrong.
So meter squared, sorry.
Apologies. Yeah, on the whole house. So that's the amount of kilowatt hours. That's only 26 multiplied by 220 gives us kilowatt hours for heating load. We add on to that the hot water load. This data, 1,700 kilowatt hours, might be a small apartment. This is right across Europe, by the way. 1,700 kilowatt hours to 5,000 would be a high-end house. Now, we do see them higher than that. I heard the other day, 2 kids who spend an hour in the shower every evening, which every now and then we come across. That's going to be higher. But if we assume in the middle here that 3,500, that's kind of a standard house in Ireland, where we don't have the previous 2 divas maybe. But if I add 3,500 for hot water, 3,400 added on to 5,700, this is 9,000 kilowatt hours. I'm going to divide that by, in this case, an air source efficiency of 400%. So the ratio of 4 to 1 that we saw earlier. So I need to buy from the electricity grid 2,280 kilowatt hours, and I'm paying 27 cents for those. That's a total of €615. Now, we might be up or down there by 10%, right? If you use a lot more hot water, that goes up. But it can't be at €900, it can't be €1,000. However, similar scenario, same size house, lots of glass, poor air tightness. This historically would have been dormer houses, typically were extremely poor on air tightness. Underfloor heating with the wrong floor coverings or something dramatically wrong, pipes wrong, so on. Undersized radiators, covers on the radiators, the same as throwing a duvet up on it. Well done. The wrong hot water cylinder, or in this case, we've just chosen 21 degrees here for the heating, so we haven't even ramped the temperature up, which in some cases, I think the highest we've seen in the last 10 years, maybe 27 degrees. So my heating load has gone up, right? So I'm now using, because the glass, poor air tightness and so on, the heating load has gone up. And because my heat pump is inefficient now because of the floor coverings or the radiators, my COP is going to be dropping here as well. But here I am now using 11,000 kilowatt hours a year. The hot water shouldn't change. Maybe we could have put it in higher there, but we're assuming the same amount of hot water. In this case, the house requires 14,400 kilowatt hours. Air source efficiency of 300. That's not even that punitive, right? We often would see it lower than that, but we've assumed here that somebody hasn't changed their electricity bill over to the cheapest rate at 40 cents. So again, bad decisions there, bad design decisions, and the house design. But that all, when we divide it out, comes to €1,900. So that's 3 times the running cost of the first one. Now, and yet there's nothing dramatic here. Okay, so we just wanted to make that point. We do hear this all the time. I believe it, by the way, all the time. But a few bad decisions are catastrophic, and people don't understand that. That's the last we're going to talk about. Sorry, what did I say there? 315% increase if somebody needed to do the maths. Air source versus ground source, just the maths on it. In domestic housing, we won't go down through what we just did above. This is a slide I stole from something else. 10,000 kilowatt hours here, we're assuming, is a kind of a standard house for heating and hot water. With an air source heat pump with a COP of 4, electricity at 30 cents is €750. If I go with ground source, I require, because I have a higher efficiency, I need to buy less from the grid. At 30 cents is €600. So yes, it's more efficient. It's saving me €150 a year. The question then is, if I'm going spending $2,000 or $4,000 or $5,000 to save 150, is that a good decision? Some people will say, I don't want the air source unit out the back. I'm happy to spend $5,000 to have that gone. The ground source unit, of course, sits in the utility room or wherever it is. But so, of course, the bigger that house gets, or if it's building, commercial building, the bigger that difference becomes in savings, and then it might become more meaningful. But people asking us today for ground source heat pumps because they don't want to go air source. When we investigate, it's because of running costs. But the running costs, as you can see here, in this case at least, is not the right reason. There might be cases where it is the right reason, by the way. So then the other things to take into consideration here is that the ground source unit will last on average 5 years longer. So, okay, it's €150 a year of a saving, but I'm not going to have to replace that unit for 25 years, whereas the air source might be 20 years, something like that. Well, that can be factored into your calculations. The ground source tends to be more bulletproof. And I'm comparing now the ground source, the likes of Thermia, Niba, or I'm going to call it the high-end ones. Even though, to be fair, there aren't many low-end ground source units, to be fair, whereas there are low-end air source units. You know, when we go to Sweden, we spend a lot of time over the last 15 years in Sweden. They talk about the disposable heat pumps, and there are that kind of the unit that you buy in Portugal for your holiday home for €700. By the time that comes to Ireland, it's $3,500 or $5,000. But make no mistake about it, that will be thrown out in 5 years, and we'll be wondering, how did I end up with such a shite? Sorry for the language. How did I end up with such a rubbish heat pump? You know, but they are there, so the air source tend to be more open to rubbish heat pumps than ground source. So the ground source is more bulletproof. Both will work down to -20. In the case of the air source,
your efficiency is getting it.
It is. We talk about that in a second, and we talk about weather data and what it means.
Yeah, just to bear in mind that time, it's nearly quarter to. So.
Okay, we'll skip on, man, Johnny. So we're into design now. So we're going to talk about here the things that maybe have hindered large heat pumps for the last 20 years. We one of the first projects Johnny and I did in England at kind of scale was a block of apartments where the consultants had used, I suppose, sizing philosophies that were fine in the past, where if I was sizing a gas boiler, it didn't really matter if it was 200 kilowatt or 500 kilowatt, it went up, I'm going to say 10,000. In our world with heat pumps, 200 kilowatt to 500 kilowatt is hundreds of thousands, okay? So in this case, we really, really, really need to understand, do we need big heat pumps or can we get away with something smaller? So the first project we did was 60 apartments, relatively small project, but it was sized at 640 kilowatts originally. The cost of that, which was actually had stopped the project, was 1.1 million. A gas boiler would have been, I'm going to say, 100 grand, I suppose, by the time all in. But the ground source, if we sized it properly, was actually 84. Now, there'll be raised eyebrows there, but we'll go through the calculations in a second. So this means it's €800,000 less. The project goes ahead, we reach carbon compliance and all the rest of it, but we'll go into the figures of that in a second. We see similar examples of this all over the place, right? 140, a lot of these big projects we did were in London, by the way. 140 apartments, 1,800 kilowatts. This was for hot water. 57 kilowatts was actually what's needed here, right? Now it needs to run 24 hours a day, but over 24 hours it can produce the required amount of energy. So, but it requires a different mindset. We can show all sorts of examples here. We often used to take engineers and so on to these apartments in Sweden. It's 104 apartments, and the hot water load was 33 kilowatt. Like, a typical oil boiler in Ireland 10 years ago for any size of house was 26 kilowatt. And here we are doing 104 apartments, hot water with 33 kilowatt. And there wasn't a backup. Okay, so these are only all examples of oversizing because we're using, I'm going to say, prehistoric philosophies for sizing of heat pumps. I'm going to jump into the one we just looked at. And here was the thinking. The engineers had actually, believe it or not, done the same heat loss calculations as we had, but they weren't quite confident with them. So they put in 60 watts per square meter, which was, look at what they call a bit of breathing space, a bit of safety. But when I multiplied it out by the entirety of the building, it came to 312 kilowatt, and they were allowing 6 kilowatts for hot water per apartment, right? And that gives another 340. And then the total size was 652. If we used the information, I suppose, that we had gathered from Denmark and these places, like Denmark has 68% district heating, so they know, not everybody will use hot water simultaneously, and they have all of these calculations for doing that. So that, they're probably a few decades ahead of us in terms of their thinking. So we used kind of the Scandinavian philosophies, and we sized. This was very simple. What was the heat loss? 11 watts. We multiplied it by the area. We got 57 kilowatts. And hot water just came out at 27 kilowatts. Right, so we added the two of those together. We got 84. Now, what allowed this project to go ahead, for any engineers that are online here, we're sweating now at 84 kilowatts. I mean, that's that would have gone into 5,000 square foot houses 15 years ago, 84 kilowatts. So just to put it in context, the engineers sitting across the table from us now are literally sweating. We still put in the 600 kilowatt boiler, and it allowed them to sleep at night, and we paid 50k for that. But they save 800k. Okay, we've put 50k to a gas boiler, but the reality is it never comes on, right? But to be fair, it's the easy way out for us as well.
It allows for a lot of what we were doing in that project was trying to get consultants to accept our calculations. They couldn't disagree with any single sum or figure, but overall they just weren't happy because I'm signing my name to this. So putting in that big gas boiler, okay, it does add 50k to the cost, but it means that consultants are happy and we've got our green target met.
Because to Johnny's point there, the heat loss, they know it's 11 watts. They know that. But when I was putting in a gas boiler, it didn't matter. Sure, why would I go killing myself on sizing something correctly? It didn't matter historically, but it really matters in our world. So they believed what we were saying to them, but when they went home and went to bed, they were saying, now everything I've done for 20 years is wrong. And it's a very hard one to swallow. I understand it, by the way. But anyway, so there's the science behind it. So now we're going to go into design maybe in a little bit more detail. Here we see a little graph actually from that block of apartments, which was in Putney in London. These were the minimum temperatures charted over a year period. And you can see here we're down to -7 in this case. And obviously you're into summer here, you're much higher temperatures and so on. The point we're getting to here in the next slide is we do get cold days, like in Ireland we don't. Certainly we're sitting in North Cork here, we don't ever, of course we have gotten -7. We don't get it as a matter of course, right? So when we look at 30 years of weather data for something like this is what our software does, by the way. It gives us, some of the engineers online here will know, but we're looking at degree day data, which gives us, yes, we do get -7, but is that, it's not like the North Pole here all the time. We do get days that are really cold, but it's not a fair indicator. We know in North Cork, its average winter temperature is 9.6 degrees or whatever it is, and that's a better indication. So when we use our software, we've just taken screenshots here out of the software. If we have, I'm going to say 200 kilowatt, or in this case, sorry, I'm lying. whatever that is, an 85 kilowatt load. I don't know what that is. It might be a school, it might be a nursing home, it might be, who knows, an office block. Yes, we've just seen here, we do get cold days, right? But it doesn't amount to an awful lot over the year, and you'll see that in 2 seconds now. In this case, by the way, the apartment block we just looked at, that your hot water load is in there as that kind of baseline, and regardless of outside temperature, you're going to need 20 kilowatts worth of hot water, let's just say. So as the weather gets colder, then you can see the amount of power that I require for heating starts to climb. But what's interesting is that is, in Ireland, is very spiky, right? What that means is statistically we get cold weather, but we don't get an awful lot of it. And you'll see that in the next graph. So this is an energy consumption from a heating point of view over the heating season. So yes, we're showing here -4. We might see -5, -6. So yes, despite the fact that I needed my maximum power at -6, over the year it amounted to very little because I spent so little time there. So most of my energy is actually consumed in relatively mild temperatures. We're going to say there from 0 or maybe 4 or 5 degrees to +10. Okay, that is not what we might intuitively predict. We might think that the cold weather is where all the damage is done. It's not, right? What our software will do then is, depending where we are in the country, it will say if this was a ground source heat pump, we will tell it maybe the rock we have, it might be limestone, it might be sandstone, it might be whatever, or it might be a shallow collector where we're inside in clay or sand. Is it wet or is it dry? What we're trying to do then is we're telling the software, I have a heating load of, I'm going to say 100,000 kilowatt hours or 5 million kilowatt hours. I'm taking this energy over the heating season. Of course, the weather data will determine the pattern of that. And I want the software to tell me how much pipework will give me 1 million kilowatt hours out of dry sand, wet clay, or limestone boreholes or whatever it is. But it's all based on data. So then that brings us on to a scenario here where if I decided, you can see here there seems to be a natural kind of a pinch point, that if I wanted to undersize a heat pump, so why would I undersize a heat pump? Well, I'm worried about the capital cost. So I don't want it to be too big because it's expensive. Heat pumps will run away 24 hours a day. They don't mind that. They don't like starting and stopping, but they'll run away. So I don't want to oversize it. Certainly, as we saw a while ago, by 700 or 800%, that's extremely foolish. But is there an argument for undersizing it? Right? So, and we would do this quite a lot. And again, the software will tell us what the cost of undersizing it is. So in this case, we've put in that the load here is whatever that is, 105 kilowatt. So it's a heating load with a base load of hot water. In this case, it's 16 or 17 kilowatt, whatever it is, flat load of hot water. And in this case, we've chosen an 82 kilowatt heat pump. So two things are going to happen. For the vast majority of the year, you can see between the bottom dotted line and what the building requires, I actually have plenty of headroom. So my heat pump is way too big. Certainly when I come out here into summer or warmer weather, the heat pump is entirely too big. It's only for a small few days in the year where the heat pump actually now is too small. And the software tells us that in this case, the red little bit there that's sticking out, the heat pump can't cater on that day. So what happens? Well, whatever we want into the software, we'll tell it, I want you to run an oil boiler. I want you to run a gas boiler. I want you to run an electric immersion, maybe. And we can calculate then, or the software calculates that if this was, I'm going to say 100,000 kilowatt hours in total, that red bit is, for argument's sake, 500 kilowatt hours at electrical cost of 25 cent, whatever that is, Johnny. It's €25. €25, good man. You sure?
No, not even very good.
Anyway, you get the point. But the software will predict what this shortfall is. Now, a lot of people will start to feel there, but the heat pump will be under pressure. That heat pump is not under pressure. It's running. Whether the building gets hot or not, the heat pump does not care, right? It's only running. We often describe that to lay people as like having a garden tap and trying to fill a bucket. There's holes in the bucket. The bucket will not fill, but the tap does not feel under pressure. the bucket is not filling, it doesn't care. So the heat pump will continue running, but importantly, I suppose, if that gas boiler or oil boiler gets pulled in, the heat pump has to control it. Otherwise, what you don't definitely want, and we've seen it over the years, the gas boiler kicks in, all of a sudden it starts to take control. It's producing hotter temperatures or higher temperatures, and all of a sudden the heat pump stops because it looks like it's no longer needed, and now off goes the heat pump until somebody tells it shouldn't be running. So we would encourage, when you go up into the larger systems, that I'm not saying you always undersize. The propensity seems to be, we want to put in a heat pump, we want gas or oil gone. That's grand in principle, we understand it, mightn't be sensible, right? You have an oil boiler or a gas boiler there. It might get, number one, it allows the heat pump to be much cheaper. And the day, God forbid, that it's really, really cold, as we saw in Cork 10 years ago, minus 17, the gas boiler helps you that day, right?
These are for kind of commercial applications as opposed to domestic applications.
Sure.
But yeah, certainly what undersizing allows is for a cheaper capital expenditure, and it allows you then on those days that you need that extra bit of poke, you pay 25 cents for a kilowatt hour of electricity. Not ideal, but you only do it for such a small amount of the year, it makes no difference to your running costs.
Yeah.
And if you saved, in this case, an example, saved 45k on your install, grand spending €100 extra per year you'd say that's good value for money.
Yeah. And I suppose the main thing is, if we're using intelligent software, this is all entirely predictable.
Yeah.
Right. So I would say traditionally in Ireland, when we were sizing anything, we sized everything for this day here, in this case, -7 or whatever it is.
And then added safety onto it as well.
Correct. And our whole philosophy is around that. When we know, and sure, of course, the minute anybody says it, you realise, okay, sure, that's stupid, of course it is, but what do we do next? And so this gives us a lot more data. It tells us what the energy consumption or how it is consumed over a heating year, over a 12-month period, and we can start to make intelligent decisions now. Okay, and it gives us great confidence as building designers or investors or whatever it is. So this is the one, I suppose we're going back a small bit now into, I'm going to say something like a poorly insulated house, or it could be something like a church. It might be a factory or something like this that is quite leaky. But to make the point, I'm going to start maybe with let's start with the church, actually. We use it every Sunday. Anybody in their right mind wouldn't put a heat pump in, and I'm only using it every Sunday because somebody told me you have to leave the heat pump on. Why would you do that? Right? If it was an oil boiler, you wouldn't leave it on all week because I need it next Sunday. You would turn it off. Now, there is a risk. When I come next Sunday now, I have to be sure that when I push the on button, that it has enough time to heat up. And this is where now we might deliberately oversize the heat pump. Okay, because if I do this on the day where it's -7 and my heat pump is designed for that day, it is definitely not designed to be starting from, from
12 degrees internal temperature and bring you up to 21.
Yeah, so you can't be on the back foot. But in mild weather, if we go back to our other graphs, you can see here that on that day, I have plenty capacity for heat up. Anyway, so what we're trying to do in these graphs is portray that if I left my house and went to work and I had an oil boiler, I wouldn't leave it on all day. But if I did, what would happen? If it's a very well insulated house, I'd be producing energy between, I'm going to say 8 o'clock and 5 o'clock that I didn't really need because it'll have leaked out of the building. Okay? Johnny and I came up with this fantastic way of portraying it here.
Johnny and I.
We're just showing that the temperature will drop in the house if I turned off the boiler, right, over the day. This is overnight, actually. And then in the morning, I leave at whatever time this is. I need heat, in this case, from 7 o'clock to 9. But if I turn off the boiler, I leave, and temperature starts dropping. And everything under that graph is energy I should not maybe have bought.
Yeah, energy that you're paying for that you're not in the house, so you're not feeling any benefit from. Yeah. So there's an argument to say that you shouldn't have bought that.
Yeah.
In that house that's well insulated, that's costing you €25 over the course of the year. So why would you bother
turning it off? And in this case, if I have a very well insulated house, I would argue what ACI are trying to push here is don't turn your heat pump off.
Yeah.
Number one, sorry, maybe number two, but number one, a heat pump should only be in an insulated house or well insulated house. I disagree with that, because that means that the houses that are requiring an awful lot of energy can't avail of cheap energy. Right? Why would that be the case? Why would,
Penalize those people.
Yeah. But if we put in, we'll say this is a stone house now with poor air tightness and all the rest of it. Everything inside these graphs now is what
you're paying for.
What you're paying for extra. So if I turned off my gas boiler and it dropped very quickly over the day, that everything inside in that triangle, as well as the other triangles, is extra energy.
Yeah.
And this is the bit that we hear about when our running costs are high. If I leave my heat pump on in this case, my running costs probably will go up.
Yeah, it'll be, that's, whereas the previous gas graph was €25 over the course of the year, that's, I don't know, €600 over the course of the year.
Yeah, and inevitably, of course, in this building as well, my radiators are probably maybe undersized.
Efficiency and
so our running cost goes up.
Yeah.
All we're saying is, and it's one of the main reasons we're doing these presentations, for God's sake, turn the heat pumps off if they should be turned off. If you would turn it off in the case of oil, turn it off in this case.
Yeah.
And there'll be people here saying, sure, I was told you can't. I know that. I don't care.
Yes.
Turn them off. There's buttons on them. There's actually a little interface on them all to be turned off. Maybe if electricity in, we'll say Denmark, is very expensive from 5 until 7 o'clock. You put a time clock on it set at 5 to 7. It blocks it out from running.
Stops it from running. Yeah.
All heat pumps come with that possibility. For some reason, ACI are saying that, I suppose heat pumps should be in good houses. Why would an old church not be able to avail of cheap heating? Fair enough, the heat pump has to be bigger, but we want to get, I suppose...
I was actually on a call with ACI this morning that I haven't spoken to you about yet, and they're discussing the possibility of allowing one-stop shops to put a heat pump in to whatever building they see necessary. What they're worried about is the adequacy of the design. Okay. So they're putting the onus on us as designers that if you're putting it in there, you better be able to stand over it, and that's where turning it on and turning it off. So they do want it in well insulated houses. By the way, that's not out yet, and I probably shouldn't be even saying it, but it is something that they're looking at doing, provided that there's sufficient design and provided there's somebody willing to stand over that it can go into the right house. So that's a great step forward, I suppose.
Well, I hope that the industry will be capable of moving with it, because it opens a can of worms if they get it wrong.
Well, and that's why they're looking at limiting it to specific
intelligent people.
Yeah.
Okay, cool. That's a step forward anyway. Hopefully it evolves in the right way. So a little bit about simultaneous heating and cooling. So here's a heat pump where I'm... Obviously, with any heat pump we saw earlier, we're taking heat from someplace. In this case, we're calling it a cooling buffer. So we're cooling a body of water here. The heat we take out of that, much like our fridge, is going in over here to this buffer. Now, I can actually send that to wherever I want. I can use it to create hot water. I can send it to radiators. I can send it to underfloor heating. I can send it to fan coils or whatever it is in a commercial building. But over here, we have we have any amount of possibilities. But when I'm taking energy out of it, I have to put energy back into it so I can take it out again in an hour. Sometimes we use that from a cooling load in a building, or it might be an abattoir or a process through the refrigeration. We're cooling, right? And then if for any reason, if I'm taking out 100 kilowatts on the hot side, and if I'm only putting in 70 kilowatts on the cooling side, I need to make up the shortfall through the boreholes. Okay, so now there might be cases, by the way, of course, if the cooling load is at some point 0, the boreholes need to be able to give me the full 100 and so on. But that's all the software, and our brains need to figure those things out as we go along. I suppose the danger here is, I suppose we were saying in the last few minutes, is that if you have the people here who have no interest in this designing it and don't understand the 12-month cycle of these things, that they're designing for only the peak, you're going to have, number one, an expensive system. It's going to be running in an inefficient way, and it was too expensive to start with. Our software, this is just a screenshot out of it. You can see here, if we're taking energy out of, in this case, what have we chosen, Johnny? Granite. So this is a vertical borehole. It doesn't matter what we're taking out, whether we're taking out 10,000 kilowatt hours or 10 million kilowatt hours. The philosophies apply. We're choosing here, we're going back to custom, we're changing the conductivity. So maybe if we know the conductivity, whereas if we just knew it was granite or whatever, we would choose granite. But you can see down here on the bottom, you can see here the active drill depth. So this tells us the amount of pipe that we need to have down into the wells. But I suppose importantly, if we go back here to, if it's limestone, it's going to be much more pipe. If it's sandstone, something similar, clay and all the rest of it, they'll all perform differently. And if I'm trying to take, in a house, it's relatively predictable, even if I get it wrong. As you go up into the bigger stuff where I need 200 kilowatt or 500 kilowatt, I better know what I'm at. Otherwise, my only option is to oversize it. We know that's expensive, but at least it won't hit the running cost. But if I undersize that and over the year, I'm taking out more energy out of the area surrounding the pipe, then it can naturally replenish because of conductivity. Well, the brine temperature drops and my COP starts to drop away fairly dramatically. So I won't spend much more time at that. I'm actually going to skip that one, Johnny, given the time. But here are projects we've done over the years. You can see here, I don't know what that is, 20 heat pumps, we'll say. I don't know, is it? You can count them, Johnny. But there's a hot and a cold side to them. Right, so in this case, the hot side is going off to, in this case, it's fan coils. So we're heating whatever that is. I don't even know what this project was again, Johnny.
Food processing.
Food processing. Okay, so we're producing heat here. We're producing hot water. We might be connected to that. Might be who knows, dishwashers or whatever it is, or tray washers or something like that. And on the cold side, then there's two things happening. Number one, there's three things happening in this case. We have energy recovery from the ventilation. So there's air leaving the building. We'll just say it's at 10 degrees or it might be 25 degrees. If you can imagine the radiator of your car sitting there, air passing over it. If we're refrigerating that as it passes, we take the energy out of it. Now, inevitably, and it's not shown on this one, but you have to clean those and it needs to be automatic. We would sometimes, depending on what's passing through, we would clean it using compressed air. In some cases, you need to use water sprayers onto the heat exchangers. But either way, we'll just say we're taking 200 kilowatts from here. The heat pumps are running at 500 kilowatts, just say. So I need to get 200 from here. In this case, I'm going to say 200 as well from ground loops. And in some instances, there might be a shortfall. In this case, we'll use open loop. But of course, we have heat exchangers, we have filtration and all the rest of it here. And we would have a preference then, because of efficiency or maybe something else. If the load drops from 500 kilowatts, for whatever reason, what do we want to continue doing? It might be more efficient to take the waste energy from the waste air because it's hotter and our COP is higher. And then our ground loop might be the next and last. The ground loops, typically the running cost of those pumps would make that decision for us. That would be the one we would turn on last normally. And that's only an example. The next one here, don't even know what it is. Is this a river?
The lake. Is it?
Yeah, it's a lake. It looks similar stuff. These are projects we've done over the years with some simultaneous heating and cooling. Or in this case, as John said, we're taking the energy from a lake. Is there anything else happening here?
Your energy recovery, your air compressor up in the top left there.
So these are the air compressors that we're essentially blowing compressed air onto the heat exchanger. So any dust that has accumulated on the fins just get blasted off every few hours, if necessary, depending what's coming out through them, and so on. We can set it up based on delta P as well, if pressure differential. Takeaways. We're done, Johnny.
Yeah, we are.
I suppose overall, in our view, keep in mind Shane is a heat pump geek here, and we believe in them, but we have to love them. They are a bit sensitive. We need to understand that, and certainly you get away with it maybe in a house if it's a simple house. If the house gets more awkward, unless you know what you're doing, you're going to start paying higher bills. Certainly, when you go up into commercial and industrial, you really want to really like it. right? But as a piece of technology, they work. Our fridges work. We don't question it. We need to start taking responsibility. It sounds like I always sound like I'm preaching to you guys for joining here and scolding you. But we need to start asking questions and being curious about it. Why are these fellas telling me I have to turn it off? These kind of questions, and that's why we're, I suppose, trying to educate in these webinars, so that people are maybe a little bit more armed, and and so on. Heat pumps are versatile, but they're sensitive. They're instrumental in decarbonisation. That's fundamentally true, and I suppose that's why we're here. For God's sake, turn them off or turn them down. But again,
where appropriate.
Yeah. And I suppose the downside to, we often ask a person who said, "I was told I can't turn it off," and we asked them, "What if you did turn it off? What would happen?" Like if the power went off, what would happen? Would the heat pump blow up? No, it wouldn't. So you can turn it off. And what's the worst case now if I go out to work and I don't turn it back on in time? The house isn't going to be as hot as it could be, and it's the same as a boiler. If I turn the boiler on back on too late, what would happen? And we're trying to get that out there to at least question it and say, well, the guy down the pub, maybe he's not the genius we thought he was. In spite of the fact he's drinking there 7 days a week. But so that's the big thing. We're done.
Yeah.
The next big events, guys. Monday, Mullingar Park is a vacant and derelict event. If anybody, I don't know who everybody is on this call, I know some of the names, but if you're engineers and stuff, or plumbers or homeowners, typically you'll be coming to see the vacant and derelict maybe. But if engineers want to come and talk to us and see about whatever, chat to us about projects, we're happy to meet you there. We do energy upgrade grants for businesses. That's on this day week, so that'll be covering the various types of grants, from obviously 0 grants up to 50% grants for businesses for anything energy related, motors, pumps, insulation, windows, and so on. There's a whole raft of grant mechanisms. So we're trying to make it simple for people to understand which one they should use. 24th of March is vacant and derelict again. Heat pump common mistakes is a more domestic version of what we've just done, and maybe more logical in some ways, because we're after hopping around a little bit on this one, guys. I hope you'll forgive. The MUD's the multi-unit dwelling. So this is for somebody who's converting something like a block of apartments. It's a 30% grant, depending on the criteria, for anything in the building, including stairwells and painting and kitchens and all the rest of it. There aren't a lot of people who seem to know about it. But if you're a not-for-profit, that grant is up to 50%. So we do talk on that. SEI, I would guess, will be joining us on that one if we can get somebody. Then we do the window and door grants. That's a hot topic since the fantastic announcement there on the 27th of January, which is after driving the whole industry mental for no good reason, in my view anyway. 7th of May, one-stop shop, pros, cons and alternatives. We talk about the community energy grant there, as well as, and we compare what types of projects will I use at one-stop shop, or a community energy grant, or a Better Energy Homes, I suppose, grant. They all have their operating envelopes, just like the heat pump. But if you take them outside of that, they seem to give trouble, and we're hearing maybe poor stories. In some cases rightly, in some cases wrongly. High temperature heat pump pilot, Johnny will be doing on the 22nd of May. I think SCI are joining us on that now as well. That's it. You'll find all those things available on the bottom of our website, ashgrove.ie. Johnny, questions?
Yeah, there's just one in. I recently spent €1,000 on a replacement circulating pump. Is that a reason for turning the system off as much as possible?
It'd be interesting to know, and what kind of, what's happening there. The heat pumps, circulating pumps are typically fairly bulletproof.
Yeah.
Right. And they don't mind running. They're built for thousands and thousands of hours. But by the way, certainly in summer, and I don't know what heat pump you have these days, and I know what you had at one point. But in summer, if you put that into summer mode, by the way, the heating will automatically stop once this is a domestic case, I know in this case. It's weather compensated. So once the weather gets warm outside, the heating system will stop. But unless you tell the pump to stop, it'll continue running. So you need to put that into summer mode. And you can certainly tell it to not run for 4 months. Now, there's a downside to that. if you didn't drive your car for 4 months and you went out to start it, it mightn't start. That pump might need a little bit of help. Just a screwdriver will start it. But yeah, that's don't know how to answer more than that.
Yeah, but probably turning on and off your heating system to save your circulating pump is probably one of the low wins you're getting from it.
Yeah, I probably wouldn't do that.
Yeah,
while I'm at work for the day and for the few hours. The good thing about tell my heat pump to go to sleep. The pump, what it will do is it'll circulate water back into the heat pump. It gives a great indication of what's happening in the house. Imagine if I were to send water into my house at 30 degrees and say it came back at 10. I would say, okay, the floor, it will assume here, either the floor is freezing cold. How could the water come back at 10? Equally, if I sent water into the house at 30 degrees and it came back at 30, well, now the floor is saturated. So the system learns a lot from the water temperature coming back. So if it actually did start to drop significantly, despite the fact that you've told it to turn off for a few hours, the system might override that and say, look, and I know you want me to turn off here, but you're going to be freezing when you come home here later on. So it might actually turn it back on. Now, I would equally say, turn it off. What's the worst that can happen here? And you get home and it hasn't started early enough. And okay, you're 1 degree, 2 degrees colder than you thought you'd be, and you put on a fleece for an hour. And there's nothing catastrophic going to happen here. And all those things, despite you'll have discomfort for one evening, but that would only be on a really cold day. If that's on a mild day, there'd be no problem. And so I suppose that's the idea of these webinars, that as a country we get smarter. These problems don't exist in Germany or Sweden or Austria. It's Ireland and England, because we don't have 30 years of heat pumps or 50 years of heat pumps like the Nordics do. So I hope that answers your question, and I've seen you on a few of the webinars recently. Give us a call if you want help. We're done, Johnny.
Yeah, that's it.
Good. So
only 17 minutes over. Well done, Chen.
Oh, Jesus, sorry guys. So after that, I've nothing to say. Only have a nice weekend, and we look forward to talking to anybody who wants to give us a call about typically bigger heat pumps. This webinar is aimed at. But if it's a domestic awkward case, give us a call as well. Okay, thank you, Johnny. Thank you, Conor and the guys. And I can see here the guys looking for CPD points. They'll all be dealt with.
Yeah.
Take care. Enjoy the weekend. Thanks, Johnny.